The purpose of this presentation is to provide the viewer with a basic understanding of surface coating methods and aspects of an operation that could affect air emissions. We will cover surface preparation, types of coatings, application methods, curing, and process inspection. Surface coating involves the application of a wet or dry coating material to the surface of another material, either for decoration, for protection against damage or corrosion, or for functional purposes. Although there is considerable diversity among surface coating operations, the basic steps involved in the process are similar. First, the material to be coated is prepared by having its surface cleaned and treated. Next, the coating is applied to the prepared surface. Finally, the deposited coating is dried or cured. Preparation of the surface to be coated is necessary to ensure proper adhesion between the coating and the surface. Typically, metal surfaces are cleaned with a detergent or aqueous alkaline solution in order to remove dirt, oil, grease, and other contaminants. In some cases, organic degreasers may be used to remove heavy machine grease and milling agents. In some industries, such as transportation, manufacturing, and refinishing, a solvent wipe may be used after the initial cleaning step to remove any traces of oil and grease that might remain. Many surface preparation operations include acid etching to increase the surface area, or a phosphate treatment or chromate conversion coating to promote good coating adhesion and provide for corrosion resistance. After the surface preparation is completed, the parts are dried prior to the application of the coating. The types of coatings used in the surface coating industries are conventional solvent-borne coatings, high solids coatings, waterborne coatings, powder coatings, and radiation-cured coatings. With the exception of powder and radiation-cured coatings, they are all composed of liquid or solid resins, pigments, and additives that are dispersed in a volatile carrier. For many years, coatings have been used that employ only organic solvents as the volatile carrier. Once the coating is applied, the organic solvent is evaporated, usually in an elevated temperature oven, and the coating hardens. These coatings have been traditionally used because the solvent evaporates rapidly, allowing the coating to dry quickly, and they produce a durable, high-quality surface. High solid solvent-borne coatings have higher solids content and therefore lower solvent content than conventional coatings. Because of the increased solids, a given quantity of the coating will cover more surface than a conventional coating and have less VOC emissions. There will also be fewer drums handled, reduced freight costs, and reduced solvent removal energy. However, the viscosity of high solids coatings is greater than for conventional coatings, which may require heating of the coating or modification of the application equipment or rate. Waterborne solvents use water as the primary volatile carrier. They may also contain 2 to 15% by volume of organic solvent to aid in wetting the pigments to enhance solubility and to promote good flow and viscosity characteristics. Because of the lower organic solvent content of waterborne coatings, significant emission reductions can be realized. Waterborne coatings have reduced flammability and reduced toxicity. They are easier to clean up, and the cleaning operations have lower VOC losses. They can also be used with higher solids concentrations without the significant increase in viscosity that occurs with solvent-borne coatings. Although water has a much higher heat of vaporization than organic solvents, waterborne coatings require less airflow in the oven to maintain appropriate humidity. As a result of the combination of these two factors, energy input is approximately 20 to 25% higher than for conventional solvent-borne coatings. Also, temperature and humidity must be better controlled during curing in order to maintain surface quality and line speed. Special care must be taken when using electrostatic application, and both application and curing equipment are subject to corrosion. Metal parts require better surface preparation to remove traces of oil or grease that could inhibit adhesion. Some early waterborne coatings exhibited poor surface quality, high rub-off, and reduced weathering properties. However, more recent formulations have a higher gloss and improved weathering properties, and shocking and fade resistance are better than for conventional coatings. Powder coatings are composed of fine, dry particles of paint solids and contain no solvent carrier. These coatings are either thermoplastic or thermosetting. Thermoplastic coatings melt when heat is applied, but continue to have the same chemical composition after cooling and hardening. Thermosetting coatings also melt when exposed to heat, but then polymerize with themselves or with other reactive components to form a surface that is chemically different from the applied solids. Small quantities of VOC, usually less than 4%, may be emitted as byproducts of the polymerization process. Because there is no solvent carrier and polymerization byproducts of thermosetting powder coatings are low, large emission reductions can be realized. Powder coatings have better chemical and abrasion resistance properties than conventional coatings. Because of the low VOC emissions, lower airflow rates can be used in the application area and in the curing ovens, reducing energy requirements. Any excess powder from the application process can be easily recovered and either reused or discarded, and touch-up of parts prior to curing is easily accomplished. However, the cost of powder coatings is higher, and the capital cost of powder coating equipment is somewhat higher than for conventional systems. Higher temperatures are required for curing, and some mixing of colors may occur during color changes. Radiation-cured coatings are composed of low molecular weight polymers, or oligomers, dissolved in monomers. These formulations contain no solvent carriers and are cured by polymerizing them with either ultraviolet or electron beam radiation. Like powder coatings, small quantities of VOC may be emitted as byproducts of the polymerization process. Curing times are very fast, a few seconds for ultraviolet radiation and a second or less for electron beam radiation, allowing for high line speeds. The operating costs of a radiation cure system are considerably less than a conventional system, and the floor space requirement is greatly reduced. However, like powder coatings, the cost of the coatings is higher, and there are a limited number of formulations. The capital costs of the coating equipment are also higher than for conventional systems, and ultraviolet and electron beam energy systems can cause injuries to workers if they are not carefully shielded and operated. After preparation of the surface, one or more coatings are applied. Typically, the first coating applied is a primer. This coating provides corrosion resistance, fills in imperfections on the surface, and provides a bonding surface for the top coat. The top coat, or series of coats, is applied over the cured primer coat and determines the final quality and color of the surface. Techniques for applying coatings include spray coating, dip coating, flow coating, roller coating, and electrodeposition. One parameter that affects VOC emissions from coating application is the transfer efficiency of the application method. Transfer efficiency is the percent ratio of the amount of coating solids deposited on the surface to the total amount of solids used. Application methods with low transfer efficiencies will use more coating to achieve a level of applied solids and will have higher VOC emissions. The basic types of spray application methods are air-atomized spray, airless spray, electrostatic spray, and high-volume, low-pressure spray. Typically, coatings are applied in a spray booth to protect the coated surface from dust and to provide a ventilated area that protects the worker from solvent vapors. The transfer efficiency for spray application depends on the air velocity, temperature, and humidity, the properties of the coating, the time between mixing and applying the coating, the surface configuration, the skill of the operator, the type of spray system that is used, and the operating parameters of the spray equipment. In air-atomized spray, the coating is atomized and propelled by forced air. The spray gun is supplied with compressed air at pressures up to 60 psi and with coating at pressures of 10 to 30 psi. As the high-pressure air mixes with the coating, it atomizes into small droplets and propels it in a turbulent mist toward the part to be coated. Transfer efficiencies for air-atomized spray application range from 10 to 50%. Airless spray uses a single fluid gun and hydraulic atomization. The coating is supplied to the gun at pressures of 1,000 to 3,000 psi, then forced through a specially designed nozzle. As the coating exits the gun, the sudden decrease in atmospheric pressure atomizes the coating, and the force of ejection propels it toward the part. Transfer efficiencies for airless spray application range from 10 to 75%. There are electrostatically enhanced versions of both air-atomized and airless spray guns. The part is positively grounded, and the coating is given a negative charge at the spray applicator. The charged coating particles are electrostatically attracted to the part to be coated, increasing the transfer efficiency over that of conventional air-atomized and airless spray guns. Transfer efficiencies for electrostatically enhanced spray gun application range from 65 to 80%. Other electrostatic application methods use spinning bells or discs. The surface of the bell or disc is negatively charged, giving a negative charge to the coating particles passing across it. Atomization occurs primarily because of the repelling forces between the individual particles and between the particles and the applicator surface. Some atomization occurs because of the centrifugal forces imparted by the rapidly spinning bell or disc. The atomized coating particles are attracted to the positively grounded parts. The bell or disc may reciprocate up and down or back and forth to allow complete coating of the part. Transfer efficiencies for applications with electrostatic bells or discs are typically 90 to 95%. Another type of spray application equipment is the high-volume, low-pressure spray gun. With this system, a turbine or compressor is used to generate a high volume of warm, dry atomizing air that is delivered to the spray gun at pressures of 4 to 6 psi. This low-pressure air gives greater control over the spray, with less of the overspray and fogging that accompanies the blasting effect common with conventional high-pressure systems. Transfer efficiencies of 60 to 70% have been reported for this application method. Dip coating involves the immersion of individual parts into a tank containing the coating. The parts, usually on hangers or trays, may be dipped individually, in batches, or by a continuous conveyor line. After the coated parts emerge, they may be held over the tank to allow the excess coating to drip back into the tank, or they may move to an area where the excess coating is collected and returned to the tank. The coating in the tank is kept at a constant solids concentration by the addition of fresh coating and solvent to make up for usage and evaporation. Transfer efficiency for dip coating is approximately 85%. In flow coating, the coating is pumped through overhead nozzles and allowed to flow over the parts to be coated. In some cases, warm air jets may be directed toward the parts to improve coating uniformity. The excess coating drips off the parts and is collected and returned to the main tank for reuse. Fresh coating and solvent are added to make up for usage and evaporation. Transfer efficiency for flow coating is approximately 85%. Roller coating involves the transfer of a coating from a trough or vat to a flat surface by a series of rollers. Roller coating machines typically have 3 power-driven rollers. One roller runs partially immersed in the coating vat and transfers the coating to the second roller. The strip or sheet to be coated is run between the second and third rollers and is coated by transfer of the coating from the second roller. The distance between the rollers determines the amount of coating that is transferred. If the second roller turns in the same direction as the surface to be coated, the system is referred to as a direct roll coater. If they turn in opposite directions, the system is a reverse roll coater. Transfer efficiency for roller coating is typically greater than 95%. In the electrodeposition or EDP process, a DC voltage is applied between the aqueous coating bath and the part to be coated. No solvent carrier is employed. The part which can act as the cathode or anode is dipped into the bath. Coating particles are attracted from the bath to the part because they are oppositely charged, producing an extremely even coating. Transfer efficiency for the electrodeposition coating is also typically greater than 95%. After the coating has been applied, it must be dried or cured. For coatings that contain a volatile carrier, this process typically begins with pre-drying or flash-off. This is done in either an open or enclosed area as the parts move from the application area to the finishing or curing oven. The purpose of pre-drying is to evaporate enough of the volatile carrier before the part reaches the oven that bubbling or blistering of the surface does not occur. Pre-drying also allows time for the coating to level itself if it has been applied unevenly. With the exception of radiation-cured coatings, final curing of the coating is done in an elevated temperature oven. To further mitigate against bubbling or blistering of the surface, ovens typically have multiple zones that operate at successively higher temperatures. As the coated materials pass through the oven, the remaining volatile carrier is evaporated, and the substrate is heated to the temperature necessary to achieve proper curing of the coating. After the coated materials exit the oven, they must be cooled. Conveyorized systems usually accomplish this by simply moving the parts through an open area, letting them cool by natural or forced convection. Paper, fabrics, and plastic films are typically passed over chilled rollers, while metal strips are usually cooled with water sprays. To review, after a component is prepared for surface coating, there are many coating types used to cover the part. These include conventional, high solids, waterborne, powder, and radiation-cured. Application coating methods include spray, dip, flow, roller, and electrodeposition. Once the part is coated, it must be cured or dried to harden the surface. There should be two goals in any field inspection. First is to evaluate the source's compliance with any rule-specific monitoring and record-keeping requirements, and with the provisions of the Title V permit. In addition, changes in operating conditions or parameters that could result in increased emissions should be evaluated. In surface coating processes, increased emissions usually result from changes in coating composition and in the method and rate of application, and from reduced performance of the air pollution control device. Recommended general inspection items include the following. Review coating composition and consumption records. Coating composition data should be evaluated to determine compliance with the operating permit and with applicable regulations. These data typically include the solvent, solids, and water content of the coatings, the coating density, and the solvent density. Coating and solvent consumption records should be reviewed and compared to any operating permit limitations. Observe coating preparation. Determine if the coating preparation area is ventilated and, if appropriate, what type of VOC control device is used. Note if the coating and solvent drums are kept closed when not being used. Observe how spills are cleaned up. Question the plant representative regarding the types of solvents in the coatings and those used as dilutants and if they have been changed. Changes in solvents may affect the performance of some control equipment. If it is necessary to confirm the coating composition, appropriate samples of the coating should be taken for analysis. Observe coating application. Determine if the coating application area is ventilated and, if appropriate, what type of VOC control device is used. Note if they have made changes in the application method. Question the plant representative regarding any changes in the application rate, since this may affect the quantity of VOC emitted. Determine if any changes are made in the control system parameters to accommodate any changes in solvents or application rates. Observe how spills are cleaned up. Observe pre-drying area. Determine if the pre-drying area is ventilated and, if appropriate, what type of VOC control device is used. Determine if any changes are made in the control system parameters to accommodate any changes in solvents or application rates. Observe curing area. Check physical integrity of the oven and oven temperatures. If appropriate, determine what type of VOC control device is used. Question the plant representative regarding any changes in line speed, since this may affect the quantity of VOC emitted in the curing area. Determine if any changes are made in the control system parameters to accommodate any changes in solvents, application rates, or line speed. Observe equipment cleaning. Determine if care is being taken to minimize VOC losses during equipment cleaning. If appropriate, cleaning should be performed with the VOC control equipment operating. Inspection of the air pollution control devices is covered in other videos in this series. In determining if a coating operation is working efficiently in regards to its air emissions, field personnel should observe, if possible, coating and composition records, coating preparation, coating application, pre-drying area, and the curing area. The inspector should be aware of the air pollution source's need to be in compliance with applicable rules and to observe the source's equipment physical condition. Coating systems have many safety considerations, including confined space hazards and inhalation hazards. Field personnel should never enter the inside of any coating system device. This type of equipment has legally specified methods for confined space entry under OSHA Rule 29 CFR 1910.146. Further training and experience will be necessary to complete all field tasks safely.